Okay.
Okay.
So, session started, and now, man, we have last session. So, what we will do today is clear up one misunderstanding that I have made yesterday in terms of multiple control constructions. And then we will focus on the Grover's algorithm. And we will do it up to the time that I will finish, because I don't think it will take full 3 hours. However, we could speak about something like, let's say, how to apply this, where could we apply this, in which mathematical fields or other fields or something like that. We could also do that at the last like 20 minutes or 30 minutes, but that is up to you pretty much. However, let's first begin with the misunderstanding that I needed to clarify. So in the previous day, the yesterday, I will minimize this window that I see here. Yesterday I was wrong about these CNOT gates with one thing. Most of the things that I have told you holds. So for example, I have told you that there is a let's say a notation where when you have, for example, more than 2 qubits, 2 control qubits, what you do is pretty much reserve something like ancilla register, right? And you make operations on this register. So for example, you control or you perform a control X, so CCX on your Q circuit. QCircuit.ccx, here are some parameters, then there is target. And these 2 control qubits are the first one, right? But then you save the result of the operation in one of the ancilla qubit. What you do then is take yet another pair of control bits and save their control status on yet another register. These start with 0, and these do not count towards your solution space. So this entire thing will be your solution space, right? Solution space. And there will be some target here, which also would be a part of solution space, because, for example, we would like to modify some qubit from the solution to actually conditionally rule out some of this 1 or 2 possibilities. So what you do here is pretty much store in auxiliary qubits the temporary result of your calculation. So this holds. Everything that I say holds here. However, I didn't tell you 2 things, because the auxiliary registers have to be cleared after the operation. So for example, if I make, let's say this will be my circuit, I will draw with the red, because this is very clear on both the black screen and the white screen of the actual output from Matplotlib. So here, for example, I have a control, 2 control qubits. I store the result in the third qubit, which is called Q2. But what happens after the operation? Well, if this condition gate holds, there will be, since we start from 0 state, this will become a 1 state. So if I want to then, there is for example, 100 other gates, right? And then I want to reuse this qubit. Well, I cannot reuse that because now there is a 1. So how to deal with this? Well, you have to kind of, after your calculation, you have to apply this entire gate yet another time to clear this back into 0 for future uses. So 0, this is clearing, right? So clear step. And then you have this quantum resource, this 1 qubit. It is now possible again to reuse this asset, this quantum bit, further down the circuit. This is how you preserve quantum resources like this. So if you, for example, would have needed to perform 100 or 200 temporary checks, you would have needed, if all of them were one single time use, you would have needed like 100 extra qubits, right? This is wasteful. So what we do is coming back to the situation with the circuit depth versus the register depth, right? This is like the ultimate kind of optimization problem nowadays. Even nowadays, it was even more crucial before. When you recall my lecture on the day first, right, when I have told you about the architectures from year 2022, this was, for example, you had like 100 qubits, but then you could have, you have to weave them into this error correction state, right? And then you are left with exactly 3 qubits, let's say. This is wasteful if I have just like a single condition and then I'm out, right? So this is so this method of applying another time the same operation clears the temporary qubit, the ancilla qubit back, and what you can do is reuse it later. And when you have 100 calculations like this, you can use a single qubit for them, right? No, uh, because you never know. Recall this, that you start from a superposition, right? So in a given shot, let's say shot 125, right? I have no idea whether this Hadamard gate triggered after the entire thing has been run through. So I can then recall that, oh, this has been evaluated to 0. Oh, this have been evaluated to 1 during this shot. After after some time passes, I perform experiment number 255. Now I have completely different state because now I could have the randomness of this could have resulted me in a 1-1 situation. What if something depends on this one? I cannot guarantee this, so I have to repeat the entire conditional operation. You cannot just X here and call it a day because sometimes this condition won't fulfill. And now at this point, let me explain to you. So Xi0 is always 0, right? So Xi0 is 0. Xi1 now could be a 0 again. And if you leave a single X gate, now look what happens. If I have Xi2, I suddenly have a 1. And further down the circuit, this one will propagate and make the entire calculation erroneous. So you cannot do this. You have to repeat entire conditional to have absolute 100% chance of, let's say, recouping this bit back and going with it further. There is, if you remember also my first day lecture, you could have said, well, you said that qubits are erroneous pretty much all the time because you have these thermal errors and so on. Even if it is still better to clear this exactly like that. Because we can manage with the circuit depth way better than just the limited amount of qubit resources that we have. We cannot make machine bigger, but we can make slightly bigger circuit. Okay, so that's the reasoning. So that's that's one thing that I wanted to clarify. Another thing that I wanted to clarify is this. I have showed you that you have your quantum register would be here, right? Exactly like this. So Q0, Q1, and I start some calculation. This is my target. So I will openly state it as a T, and I apply X here, right? Conditionally. Okay, you say that's fine, but if you look at this circuit very closely, what happens is that this gate only activates X if and only if Q0 is 1, right? And Q1 is 1. What if I wanted to do any other combination? Because now I can only express one single combination, right? I can only express a 1-1 like this, and I can only check against 1-1. So this is a problem where I could actually perform any combination, and this is how you do it. This is the solution to do. For example, if I were to check whether I have a 0-0 in the circuit, then I cannot change my control qubits, right? This gate cannot change. This gate cannot change. This is like set in stone, right? However, what I can change is the surroundings. So for example, what I could do is I could append here an X preemptively. And now if I append an X here, I will negate the 0 into 1. And now this control will be fulfilled. If I want to a 0-0, I have to append yet another X in this position. Now I can check against a 0-0 circuit. I mean situation, right? So if my quantum register is a 0-0, I can check this now. Okay, so that's nice, but this circuit is odd, right? Since it has the operation at the end that is also an X. This is because we would like to preserve the same state before and after the operation. So even if I reflect over the other axis, so this X is reflection over Y equals X on our unit circle, right? If I have some state here I reflect over the y equals x into this state now. I will mark it as red. Oh my God, I have removed everything. I'm sorry. I mean, I could just do this. Right. So this one. Crap. Okay, so I reflect my blue, my small blue qubit, and this is my temporary state during the calculation. So this is my temporary state. I perform a calculation, some papapoop, and then I want to go back to my original state for further calculations. This is why we have this construct, this entire construct. The X gates before our conditional, and then X gates after the conditional. Because this is like a preparation. This is preparation, prep. I will call it prep. Operation, so op, and reversal. So this is the clarification that I wanted to make. In other words, you can have any combination. If you append a single X gate on any of, if you apply a single X gate on any of these qubits or any combination of X gates, you could express any combination of bits, let's say 0, 1, 1, 0. In terms of 4-qubit gates, we could do 1, 0, 1, 0, right? So in this qubit, so qubit 0, this is Q0, right? Q0, Q1. I will mark it also as green. So this is Q0, this is Q1, this is Q2, this is Q3. So if I want to prepare a gate for this measurement, if I have actually state 1010, if I actually have a state 1010 in quotation marks, because this isn't a decimal, then I would apply as my prep operation, I would apply an X gate on Q0, right? Q0X, and Q2 also would have an X gate appended to it, or rather applied to it as a preparation and as a reversal. So that's the clarification that I wanted to make, because I didn't mention it, and this is how you perform these calculations. I am sorry, yesterday I had very, very busy schedule during the workshop day, because I wanted to show you many things. I wanted to show you, the differences between Qiskit 1.0, Qiskit 2.0, and other, let's say the C underscore if operation, how you could do this in Qiskit 2.0 if you were unfortunate to download it, and so on, and other operations as well. For example, the seed simulator setting, and so on. I have just I was lost in my explanations, but this hopefully this is a nice way to clear out this misunderstanding, and we can go on further. Okay, so are there any questions to what I have said? I don't see any questions, so we can go into inversion about the mean. So First of all, a little we will take a little discourse. I mean a little let's say we will divert from the Grover search into some kind of a land that will establish the general intuition for the algorithm and what it does, and then we will go back into quantum and we will implement it. So first things first, what uh, operations do we use during the Grover's algorithm? The Grover search is an algorithm that searches over the unstructured dataset. So in other words, in a regular, let's say, in regular searches, when you would like to do, let's say, an array, right? 1, 2, 14, maybe you have 9 here, maybe you have something like 27. Um, if you wanted to search through this entire list of numbers, um, what is the best way to do it? Well, the best way to do it is just sort it, forget about it, that you have sorted it, and then use the binary search. This is pretty much the standard, even on, they teach you even on lead code if you want to do this. But uh, this is the classical way, right? And the search, the sorting algorithms usually have a complexity of O n log n. This is like a pretty much standard complexity that you would like to that you would expect from a search algorithm. There are very let's say very the best scenario is like O1 or let's say ON, because you just want to search through it, search through the entire list and just check it once, right? Every single element. And this is what you would do. However, in quantum, we can do better. Since, for example, when we have uh, our search space, right, with all the H qubits, all the H qubits, there is, this is pretty much, since we do it at random, this is pretty much like a unstructured data set. We each experiment we get something else. We have n amount of these gates, which amounts to 2 to the power of n search space, right? And what do we actually do with this? How do we go about searching in this space? We cannot really sort this in a regular way, but what people have found is that after applying some operations, you can boost the chance of finding your wanted element while lowering. So, for example, there is, let's say, let me use yet another similar list. So I have 7, I have 23 now, and I have, let's say, -10, right? What I could also uh, showcase as another way to represent this entire list is that I have some collection of wanted elements, and let's mark it as W. So this list would be, let's say, 7. And I have something like unwanted elements, and this is the rest pretty much. So there is like 1, 14, and so on and so forth. So it turns out that in the quantum world, because I operate on probabilities, I can have a I can boost probabilistically the chance of finding this experiment to be success, and lowering all of experiments that have this as output number as success during the operation. So in other words, what I can do is I can try to find 7 in my algorithm much more often than any of the other unwanted answers, right? Um, and this is how you do it. So what we need is one of the operations that we need is inversion about the mean, because what we do is pretty much we try to perform a certain operation that will mark our elements as wanted during the calculation. So for example, out of this 1, 14, 7, right? I want to mark 7, marking process, let's say, I don't know how to, I will do this. Mark 7 as wanted, and then make an operation so that this make an operation which boosts the chance of finding the 7 after performing my algorithm. So this is what we do. We usually mark here, for example, we have a task 1. This is also the last thing that I want to mention. The notebooks for today, uh, we mentioned the multiple control constructions, so this is Q80. And then for today, there is notebook Q84, Q88, and Q92. So pretty much the last 3 will be used today. So what I can do is do something like this. Let me first instantiate all of my elements. For now, these will be, since we now diverted away from quantum at first, uh, no worries. This will be very, very close to what we will do in quantum. However, we have a weight of 1, so every single one of the answers that are in our, let's say, a search space have the equal probability. This is the weight. This is not the probability, because some of all of them, all of elements will equal to 8 if we do this naively, right? And this is not true for the probabilities. However, first let's say represent it as the equal weight of all the states as our initial moment, as our initial state. Equal probability, equal weight towards obtaining any outcome. Let's say this is a fair K8, right? K8. If you played some, I don't know, Warhammer, or like original Warhammer, or for example, Dungeons and Dragons, then you probably uh, know this definition of D8, which is dice with 8 sides, right? Dice with 8 sides. every single side has an equal probability to be thrown out as a result from 1 to 8. So what do we do? Suppose that only our fourth element is marked. So what we could say is that, okay, we have equal probability of having an each outcome. Then what we usually do is we want to mark something. And how do we mark? In this scenario, we mark by flipping the let's say the phase of this. So the probability will be the same, but we flip its phase, and this is how we mark it. Then what we do is we perform something that is called an inversion. So over the mean. So how do we do this? Um, we have to code it. So what do? We do it this way. So calculate the mean of all values. So, well, okay, that's not that complicated. We have a mean equals, okay, so let me run this again to make it actually in our memory. Let me run the cells. Okay, so let us sum over the elements and divide it by the total count of these elements. So we could say len elements. So this is our mean. The elements are our weighted probabilities, let's say, right? So these are the weights. We sum the weights, in other words. We could also print this result as f string, open the curly braces, and then mean equals close brace, close quote, and the end thing. Okay, so here I didn't change anything yet because we would like to reflect over this mean. So how do we reflect this over the mean? Let's say that we have these states. I will draw them as a big block, let's say, with only small fraction as our actual wanted answer. So there was 1, there was 0, and there is -1. The mean is 0.7 point. So it is somewhere here. And what inversion over the mean does is that if I have one of my, let's say this will be the one, the probability, the weighted probability of obtaining a 1. What I do is for every single of these elements, right? For every single one of these elementary outcomes, I take its weighted I take its weight, then I reflect it over into the resulting state, which will be here for the one outcome. It will be 0.5, right? And then I do the exact same operation for every single one of these. Oh, this actually turned out to be pretty nicely wrong. So I do this for pretty much every single one of these operations. However, once I get to this point, let's say this was my fifth element that I wanted to mark, then as you can see, we reflect in this direction. And since we talk about the reflection, we boost the chance all the way up here. So in this case, my resulting state after this operation would not be some measly like 1/2 or something like that. It would be something way bigger. Like here, I think it will be like 2.5 or something like this. Because we have my initial state, which is -1, and then I have to take twice, I have to add twice the negative difference, right? So twice the difference. I mean, we could take the absolute. Let's say this would be the like ABS div. Uh, and here, if we are above, we take a negative of this absolute div. So what we have here is that I have at the my div is exactly of my original -1, and also this fragment that I have been missing towards the 0.75, so 0.75. So this will be a difference of -1.75 compared to my mean, which would be a kind of like a 0. So after the reflection, and we will actually calculate this right now. So elements will equal to, oh, will equal to what? Let me actually redraw this in the for element in elements. Oh. So what we do here is we calculate the difference. So diff is my mean minus my current phase. So this would be the element, the weight of my the weight of my outcome. Here it is 4. Okay, I have presented to you the case with 5, but it doesn't matter. We could actually select a 4. So this would be our diff. Then what I want to do is I would like to append to my new outcomes the result of my current element minus 2 times diff. This should give us the good result. And let me run this. Okay, I have messed up. Plus, I think this would be, yes, this is the right way to do it. So as you can see, this was our these were our initial states. So let me throw them back, right? And this is my marked element. Let me draw it in yellow. Look at how much or more often, if this was my original probability, oh yeah, it doesn't actually keeps it. So here was our, and this was our marked element. So this is the red line shows our initial state, and the yellow dot marks our element that we strive to search for in this list of numbers. Now we get if these are the weights of probabilities of obtaining our result. Now I have a biased dice, biased D8 dice, right? So I have a situation where my state vector would be something like this, 0.5, something, something, something here, right? And at the element 4, I would have 2.5. This is very nice because I can get my searched answer way more often and don't require as many experiments to find this answer if I fail to find it at the first time. So this is the idea behind the inversion over the mean and what it actually does in terms of its let's say uh, outcome, right? And we can repeat this over and over and over and over again all the time. I will jump into this solved notebook to give you the idea of what do we actually do when we apply this way more than just a single time. So here, as you can see, this is after the second time, right? Our probability has grown even more than previously because this is like what 2.75, 2.75, and these went into negatives because their phases flipped due to our um, our mean being pretty much at the bottom because we had like one half. All of these targets were previously one half, and we pretty much flipped over the mean, which was very low, like here. Let me let me print the mean for this. Okay, and we will rerun every single cell, run all cells. So mean was 0.18. Okay, 1 over 8. And when you have when our weights were at 0.5, which was 1 over half, which is 4/8, then we subtracted minus 6/8, which lead us to negative quarter, right? Negative 0.25. And this is how we land in the negative phase. Recall that this isn't actually the real probability. That is why it is okay for this mock of a process to have negative weights. Also, there is a question. Yes, it is exactly something like this, right? So when we establish a mean, and then all of the values that are up gets pushed, gets reflected over its own value relative to this line, right? And if I start through this, let's say this middle line, so let me rephrase that, right? Let's say this is our mean. Suppose it completely, this isn't our mean in this case, right? But let's suppose it is. What happens is that I see that, okay, this ends here, also supposedly. So I reflect it over this line somewhere here, and my new state would be like this, right? Because there is 0 level. And then all of these states that were left out here, if still the red line is our mean, if these were to reflect, they would have gone up all the way up here and reflect over this side, right? So this is kind of like a mirror. Imagine yourself seeing you in a mirror and thinking about the total distance that you have not only to the mirror, but to your other half that is on the other side of the mirror. Okay, so this is how so this is this push force that that you imagine in your question, right? This is how we act. But yes, that's one way to describe it. So here, for example, we also have a yet another operation, and from recall that there is yet another thing that you would like to actually know about. Here on this chart, we do plot something else, because we do plot what happens with this one element after every single iteration. So this representation was about all the elements, how do they interact with each other. Now let's focus on a single element, which is this one. What happens to this one element during this operation of inversion about the mean? And after each operation, when we apply like tons of it, to a ton of times, let's say 20 times or 30 times, what does it do? Well, it turns out that it doesn't do very well, because uh, recall that this is about a relative probability, right? So we top out pretty much in the same spot, or close to the same spot. There are actually some small differences, but we top out here. But after, this is iteration 1, this is iteration 0. Sorry, this is our initial state. So I will call it a 0 here, right? So this is the state 0. So this is initial. This is iteration 1. This is iteration 2. Now we did a boost the relative probability of having our answer. We then boosted the same. We did boost it yet another time. However, this is insanely minuscule change compared to our initial step. If I go further, however, I lose on my boost, and then I lose it so much that it actually becomes even worse than it was at my initial uh, stage. So even if I have my initial state as 1, here I have a minus like what 0.25, and a this is a warning for us that we cannot actually apply this as many times as we would like. It is not like the inversion about the mean method to boosting our chances of finding wanted outcomes does not function like, let's say, regular deep neural network, right? When we have just a gradient descent and whatever the iterations we have, like whatever the energy we would like to burn, we can burn the sun. And if we want it, yes, we can get this straight little 0.00001% extra accuracy if we want, right? In the training set. We can do this. This is the CNN, or for example, CNN or DNN, so deep neural network, right? CNN convolutional. This is not like this. We can overestimate, and this algorithm only works up until the time. Of course, we could go back yet again, right? This is in negatives, but we again have minus 0.275, it turns out. Uh, Quite close to it, it seems. Which, since this is relative probability, it would give us the answer again, the same amount of time that we want. So very much. But we wasted a lot of time to reapply the algorithm over and over and over again, where we could have just stopped here and take the best result. So this is very important outcome as well, because this is a real problem in either the quantum state. This is how Grover's algorithm actually work, that it boosts in quantum hardware, it boosts our wanted outcomes, and it does have the same drawback, that we cannot repeat it as many times as we can, uh, and as many times as we afford, because we overshoot. We can overshoot. This is how we can state it. This is the effect of overshooting. So this was the case of a single value. There is yet another depth. There is another layer of depth to this algorithm. So this is some iterations for one element searched and searched in a space of 8 elements. So recall dice, 8-sided dice from Dungeons and Dragons, pretty much, right? Space of 8 elements. However, what happens when we have more elements? Or we search even more elements from the same amount of space? Or we search more elements, but we have huge space? So what is the interaction here? There is a nice, uh, there is another chart for you that you can watch, and here actually what we have is quite different situation. So this task from 84, from notebook 84, is about 16 elements and one element searched. And then we could actually make even more operations. And here we have a text that represents the actual Grover search algorithm. So we will so we will go towards it slightly later on. So let me load all of this. So here, for example, what we have is a task free, sorry for scrolling. So task free, N16, so we have double the search space, and we also have one element. And look what happens. This is our initial state, and this is our state after the first boost. The relative probabilities are fine, go up to 4, but remember that we have double the space. So this even if the multiplier is twice as big, so previously we have went from up to 2.75. Now we go into multiplier of 4, right? But the space is not 8 elements, but 16 elements. So this will get diluted in the space, in the state space as well, no matter what. So even if we have a 4 time, even if we are, let's say 4x as likely, the other elements will have other certain fractional probability to their own outcome that will sum up, and there is 15 of unwanted answers. So even if that fraction is very small, it gets multiplied by 15, right? Uh, so that's really something that we should be aware of. And here, look at this. To get to absolutely top probability, to absolutely top relative weight in our dice, let's say, we have to perform more operations of the inversion about the mean to actually get to our best probability scenario. But we also could have stopped slightly earlier and also be content with this one. So that's the case. Okay, so we could draw it for other cases. For example, here we have, let's say, the entire state space is 16, so the same as the previous example. But now we mark 3 elements. So what happens when we are okay with having more than one element? Well, it turns out that we don't even need that much operations now. We only need one, and that's it. So the the more space, uh, the more, let's say, solutions that we want, that we are satisfied with, are there in our solution space, the less iterations we would like to apply, let's say. So that's the kind of like the gist of it, right? So if we have, for example, go from one solution, one search solution, into three, and the space is in both cases the same. So the case 1 and 1 is equal to n2. We need less less Grover iterations and inversion about the means iterations, because this is the center element of the Grover's algorithm. This thing about inverting different weights of probabilities of our outcomes. So iter at free searched is maybe not sharply less, it's just less searched, is less than iter when iterations when there is only one searched element. I absolutely mess this absolute mess. Okay, I will just write one there and just paste it out. So this is the gist of it. If we have the same amount of search, let's say 2 in both, right? So this W wanted is in both cases the same, wanted 1 and wanted 2, but the number of 1 is, let's say, uh, less than number of the number of 1, our total search space is less than in our second case, then we would need more iterations for the second operation. So the iter 2 is greater than iter 1 to arrive at optimum scenario, to arrive at optimum probability. So the bigger the space, the more we need to the more we need to search, the more we need to apply the reverse iterations. The more solutions that we have uh, in our space, the less iterations that we want to apply, because we can be satisfied with just finding one of the answers, and that's it. In general, there is a nice way to describe it, because the entire complexity of the Grover's algorithm is of O square root of n. Why isn't it better? We could have, for example, said that, oh, we search through 2 to the power of n. Why don't we have a, let's say, log n, right? Search. If this was the case, there is a funny outcome that I have read prior to this QBronze, and this would be actually, I will show it to you now. Google, let's say Grover's algorithm speed up. So only it is said that it only provides a quadratic speed up. If this was an exponential speed up, this would have mean that pretty much this would be like NP equals P. And it would be insane breakthrough in everything, but it isn't. Unfortunately, it isn't. But it is still a very, very good outcome. And there is a reason for it, because we, for example, we could say that, okay, we have expand our solution space like exponentially because we apply yet another. We multiply by 2, by 2, by 2, by 2, by 2 with every single qubit. And this grows exponentially. Our search space grows exponentially. But then we have uh, counter we have countered this by inventing this Grover algorithm, if this was if this was true, and we could have done pretty much insanely many things. I think, and this would mean all of the some of the other proofs that are yet to be answered, also become pretty much uh, answered right away. So this is the geometrical meaning of what happens on the actual quantum hardware. We are going to get to that right now. So for so in this but first of all, let's finish with this, let's say, with this notebook. So we have shown that the inversion is a nice way to boost the probabilities of wanted answers. And also we established that the Grover's algorithm provides a quadratic speedup, which means that it is like, um, let's say, we could apply this operation square root of times, square root times compared to our search space. That could be kind of like a, let's say, here is a good answer. This is the complexity. Right? This is the word that I missed. I'm sorry. I sometimes lose. Let me also change this color to green so that you can see it actually. Yeah, so that's, oh, and the oracle. So so that's nice. We have the inversion of the mean. Okay, but how do we actually do it in regular scenario? Well, there is a thing that is, we need to first find a way, because it is all nice and dandy if we speak about some, let's say, bar charts that flip their sides and make nice comparisons, nice charts. But how do we actually mark our solution in practice, right? And this is where Oracle comes in. So this is a special function that will mark by either 1 or -1. In our Oracle, there was this operation of inversion, right, which we just multiplied by -1. In Grover search, it isn't like this. It is something else, and we need to worry about the actual matrix, which we multiply entire register, entirety of our register, or part of it, because we could append these ancilla qubits and so on, and these also will grow our matrix. But if we construct this matrix properly, this will be our oracle, right? This matrix that will act on our state C, and it will modify it to be some C1 that will have probabilities of our answers boosted. So this will be our state vector where, let's say, this one probability would be boosted, and this all of the and these all other probabilities would have been let's say downsampled. I don't know how to downgraded. I don't know how to properly say it. I lost the word in English, sorry. So this would be it. And in terms of quantum, we just deal with the amplitudes, right? So that's what the next notebook that's where the next notebooks comes in. So in terms of let's say that we have three different qubits, right? And we want this is pretty much mirroring the situation from the previous notebook, but previously we used kind of like weights of probabilities that are on the dice, on the fair die from um, Dungeons and Dragons, right? So there is like this die is made from triangles. If you play, then you probably know this. This is how it looks like, and it has, for example, like 7 here, right? Octahedron. That's I think the name of this shape in 3D. So recall that coming back to our quantum state, recall that each of these bits is like two-dimensional state, right? Right, 1, 0 or and 0, 1. We need to search for three marked elements in the space of 8 elements. This is literally 8-dimensional space. So how can we even display on in our mind how we can reason about it? Well, there is a nice way to do it, and it is to actually perform a linear combination of all of our wanted states and yet another linear combination of our unwanted states. If you do this, notice what happens. I have these enormous vectors, right, with 8 entries. But if I sum up 5 of them into one, then I get one vector, right? If I sum up 3 of the ones that were left, I get another vector. And these two vectors are orthogonal to each other, which means that when I take these two vectors combined, so the combined probability of my wanted states and combined um, probability, or rather amplitude in this case, of my unwanted states, I can represent it, since I have now two vectors, I can draw a normal, and suddenly I have a regular plane, regular two-dimensional plane. So now it means that we could reason with it on a unit circle, because unit circle is exactly two-dimensional plane. This is a very neat trick to make 8-dimensional problem way easier and represent it on as a two-dimensional, because it actually we can do this since we group our states into wanted and unwanted ones anyway. Um, and this is how we can present it. Our vector in 8-dimensional space that will mark a slice, a hyperplane in this 8-dimensional space, like something completely unimaginable, it would seem, suddenly becomes very manageable. This would be our marked, this would be our unmarked state, and this would be our marked state. Notice that we could actually also represent a global phase like this, because we still are in the uh, quantum realm, but uh, and because of that, we could actually mark a minus and minus marked and minus unmarked. So this entire vector that has 0, 0, something, let's say I will draw it as S, S, and S, then 0, 0, 0, 0. Did I? No, I messed up and I drawn one more than I need. This will be our wanted state, right? So our marked elements, I'm sorry, marked elements and unmarked elements will be this one. So let's do it as A. A, this will be 0, 0, 0, and this there will be also A, and A. These will be coefficients that, or rather amplitudes for these states. Now I have two perpendicular or orthogonal or mutually exclusive. You could use any term of any term like this to internalize this. So these will be our unmarked. I have two vectors now. I have two vectors, and I could just uh, combine them linearly to make the combined reduced space and represent it in two-dimensional plane. And this is actually really nice to simplify the reasoning for ourselves. This is here in the notebooks, you actually have this uh, pretty much drawn out in terms of mathematics. You have tensor products. You have this presented to you pretty much in plain sight. So what you can do is also calculate it yourself or look at the equation. I have given you pretty much the intuition on how to go from 8-dimensional unreasonable to, let's say, unreasonable to visualize space into our easier to visualize space. So that was my aim to show you. This is the way to show you by pure pretty much mathematics and deliver the proof that we can do this. Here there is a slightly different choice of elements, but that's okay. This doesn't mean anything in terms of the usability of our Grover's algorithm anyway. You could pick any number of elements and it would mean the same. This is something that this is very tricky question to answer, Robert, because we do not usually know in terms of our business problem. Okay, because this problem, what you see here, is a toy problem to make it to let you realize how it works, right? But in our business problem, we have in simplification, I need some darker space, more of it. Okay, this is fine. So, for example, let's say that my green qubits are my so my let's say qubits that represent my solution space. So what I do, usually what we do, the entire scheme is that we need a marking phase exactly as we said in notebook 84, right? We need a marking phase, M phase, uh, M phase, and then we need a inversion phase, so I phase. Don't be confused by the name. In this term, um, I will use yet another term. I'm sorry. This is bad naming. Let's say marking step. Okay, step. Because this entire thing, this entire operation, on the this will be our start. Uh, let's do it even further. You know. And let's draw this with blue colors. So here are our qubits, right? So we need a prep phase, yet another P phase, P step, preparation step. Then we need marking step. Then we need inverting step to actually apply this inversion over the mean, right? And then we reclaim results, let's say, right? So result step. And this is the time axis of our algorithm. This is how, for example, the gates are applied on the machine. So in preparation, we apply H tensor N on every single qubit that we have in our solution space. Why? Because usually this is what we do. Okay, so in terms of the searching for integers, let's say, right, that correspond to our solution, here we do this. The preparation step could be something different in terms of your business problem. The preparation step could mean something different, but in here, our business problem is to search for integers. So it actually is worth it to apply Hadamard to every single qubit because we get a superposition of every single integer that we could possibly have on every single qubit. So this could be like something small, for example, 2 to the power of 4, because we have 4 qubits. And then we apply 4 Hadamard gates to prepare this algorithm. Then, and this is because we search for integers, as we said. Then what we have is, oh, there is actually, sorry. So then we go with our qubits into the marking step. And this is where the gigantic, enormous operation called Oracle. This is the name that people use and what we use in this series of notebooks. So Oracle, Oracle. So this is our f of x, let's say, function that does the marking. And answering your solution, this is how we mark. And if we are designers of Oracle, we could get an idea of what is getting marked, but out of of these states, for example, here we have a measly 2 to the power of 4. Imagine that you have 2 to the power of 70 possibilities, okay? And how do you know which one of them is getting marked? There is very little that you can do. There is something, and in Q nickel and Q silver, you have the method to actually guess the amount of solutions. There is that possibility even after applying the oracle once. But before you apply oracle, and even slightly after, whereas when you just play with the solution, you don't really know the amount because um, because of the complexity of the oracle, for example, that you might want to search. And if it is a fresh problem, there is no one to tell you the amount of solutions that you can do. Then so that's the oracle step. Then we actually invert with yet another matrix. We perform an inversion. And this is the probably the most known operator here. This is a Grover's operator. Uh, Grover's operator. And it does perform, it is a construction that allows you to perform the actual inversion. And after the inversion, let's say the probabilities are already altered, so you could do some post-processing, for example, swapping the qubits between each other to fix the let's say fix the ordering or something like that, because there is a slight problem with it sometimes. But in other words, here we measure. Here we measure. So you probably are already familiar with this operator. Here we measure our entire state. So this is the complete like view of this Grover's algorithm, how it looks like in terms of operators from a bird's eye view. Um, so this is that. And a nice thing is that, okay, uh, there is, let's say, yes, this is the magic of quantum computing, because this is like, we don't need to perform a ON, we perform O square root of n in quotation marks, because there is like a slight multiplicator with like pi over 4 or something like that. But it in terms of complexity, when you have some constant, you throw in the constant into the complexity and the constant vanishes, right? So in complexity, it only means that your square root of the search space, right? So and in yeah. So that's the result. And now, what do we do here? So how do we actually um, perform this? Here we have simple visualization of the algorithm that is going through a quantum state. This is how it is done in terms of visual representation on a let's say on our unit circle, right? That we are already familiar with. So this is our initial step, and every single step, as you probably can see, rotates us by a single angle around the unit circle. Here we apply it 5 times, exactly like previously. when we applied it several times to search for the best amount of iterations and to search for um, pretty much the answer for a question, what happens if I apply it several hundred times, let's say. And it turns out that we are in a really bad spot if we apply it too much. So this is exactly what happens in actual quantum realms. So we actually rotate. If we have applied it yet another time, we would have rotated even further into unmarked again. So it means that our probability of having an answer represented by one of our states from unmarked will get boosted, right? So here we boost in the other direction. We first boost in our wanted direction, but then we boost into our other direction. But on the unit circle, we see that it actually means that we rotate every single time around the unit circle. And and if we were to I will actually run this. Each each um, each of these operations. You could run this yourself. This is Q88 now. So what do we see in terms of geometrical meaning of the unit on the unit circle? Because I told you that this is a rotation, right? This looks like rotation, but there is more to it because we could actually disassemble this entire operation. This is for now. This is virtual. This is a visual operation. We will get to how to code it for a certain case in the notebook Q92. But for now, let's look at the visual representation. So here's our Hadamard gate, right? Um, this is pretty much. Oh wait. Yeah, so what we can see here is that is the, let's say, the explanation for how to, let's say, represent it geometrically. So in the first case, we draw the initial state. We draw our initial state, and we draw two lines that will represent something that we will get to very shortly. And the first one actually happens already. So if we describe every single sub operation of the Grover's algorithm, this is what we see. First, we preparate. God damn it! I have troubles speaking English because I lost the words in the middle of the sentence and I have to think about them. I'm sorry for that. So what we see here is that we first represent two lines. One line is exactly aligned. Ex it is aligned exactly as our initial state after the first preparation. Because first we have a zero some amount of qubit zero state, right? And then we prepare a pretty much plus all the way down to our last qubit plus, right? So this is what we want to prepare. This is what we want to prepare because we apply the Hadamard tensor n state, right? And this reflects, and this is our marking, right? So first we don't apply any marking. We apply some marking, and then what? It turns out that the first operation that the Grover's algorithm does is it reflects our state over the x-axis, so over our quotation mark x, because, like, for example, if we draw it like this would be x, this would be y, right? So it is kind of like x because this now is unmarked. This isn't our regular zero. This is not our regular zero. This is like probability of relative zero towards not finding any of our solution. We have 0% chance of finding 0% chance of finding um, answer. This is the unmarked state, complete unmarked state. Um, so what Grover do is that it reflects over this unmarked state, and it applies yet another reflection, but it applies a reflection now over our marked over our state after the marking. So it very quickly boosts our chance of getting any marked solution. And this is how we propagate further and further and further with each iteration. Here we see iteration 2 when we reflect again over this line, right? We see that we are pretty much like, no, we are on the minus. We are on the actual minus. Like in quotation marks minus. However, when we apply yet another, when we finish the iteration, we are even closer to the marked state. And this is how we can geometrically reason about this algorithm. Here is also a, let's say, a notation-wise operation presented to you. There is yet another thing that I didn't showcase you when we were at the day one, which is that we always written these ket vectors, right? Like this, but there is another notation, which is this kind of like inverted ket vector, and we call it bra. And this entire, with those two, we call it a bracket notation. Bracket. I should have told this at the beginning, but what it actually means is nothing more than the bra being, let's say I will mark it as A. The bra vector is our A vector that got complex conjugated and transposed at the same time. So this is the meaning. So it is a row vector now, which has, for example, 0 0.5, 0 0.5, 0 0.5, and so on and so forth, right? The amplitudes. So this would be some sort of a state of 2 qubits. This would be this bra vector, but yes, this would be this bra notation, and this is a row vector now. So in terms of what are the implications, we get the same implication as I have told you in terms of the vector and vector transposed. For example, when we multiply them together, which we will get a rank 2 tensor, right? So this is rank 1, rank 1. This is also rank 1, but this is transposed. I have told you about this at the first day, and then we will get a rank 2, which is a matrix. And there is one other thing, that when we do a something like this, so bra and cat with the vector of itself, with the vector with itself, it goes to 1. Why is that? Well, it is very simple to answer, because when we recall the vector transposed and vector, it was a norm of a vector, right? But we all already know the norm of the vector in our representations, because the norm of the vector is its length. Length, but we always want to preserve the length as equal to 1, because this represents our total sum of probabilities, and it never uh, want and it is and we always want to have it as 1. So if you see something like this, right? This a bra multiplied by a cat, it is a 1. And here it actually is the case. For example, here we do have this this will be equal to 1, let's say. This is the perpendicular vector, so it will be a 0, because we have the there is no vector component for those 2 vectors that is in the same place. So we will get, for example, like 1, 0, 0, 1, but we will get a multiplication uh, with the bra like this. So multiplying 0 by 1 will get 0, 1 by 0, 1 and 0 will get also 0, 1 and 0 also get 0, 0, with 1 get 0, and the end product of this operation will be 0. So that is why you also have this shorthand notation for this for these operations here. So that's a little explanation about what the notation in this notebook mean for you, so you won't get lost. And the I, of course, is the identity matrix. And A and B are our respective probabilities of having certain states of A, which would be, let's say, marked elements, and B, which will be the amplitudes. Sorry, here we say here we state it for the actual um, quantum. Uh, Here we actually stated for the quantum states, so we deal with amplitudes. Right. So that wraps this up in terms of Q88. We could go to Grover search implementation, but I first would like to have some break, let's say 5 minutes for a quick, let's say grabbing something hot to drink. Uh, I have a problem because It's cold in my house, so I will grab something hot to drink for sure, or use the bathroom. Um, I think 5 minutes will be enough. So let's say to 1957. So 3 minutes until the full hour. So GMT plus 200 break until enter. Okay, so that went into the chat, and we can meet in 5 minutes exactly. Okay, so I am back. Uh, and here we have it. So the last notebook, the implementation. For this implementation, we will require exactly the same thing as I have told you about. So first, the prep step, prep step, then the query. So this will be our queue, or we could say this as a oracle or whatever. Um, oh my God. Okay, so our queue, which is the query step, invert step, right? So this will be invert step, and then measure. So this will be the G matrix. This will be an H matrix, right? And there will be a measure at the end. And there are some qubits here. So the first things first, is the easiest task for us, which is that um, we would like to have some certain, let's say, uh, this the certain superposition of all of the states. This is very easy. This is not done in the tasks anywhere besides the last step of this notebook, because we have already been doing this throughout the um, let's say throughout this notebook, throughout all of these notebooks, many times. It is very easy. We just apply uh, h tensor h tensor h on whatever the qubits we have. So these qubits will represent our solution space, right? So S space or search space, and there is a also sorry, there is also I, tensor I, let's say something, and this will be our ancilla qubits, for example, right? So A qubits that we would need for other calculations, temporary calculations within the circuit, ancilla qubits. So that's the initial step, but first, the most interesting part of it is the query and the last inversion operator. So there is a notation told in the notebooks that we just go from the let's say product space of exactly two outcomes 0 and 1, and it will be, since this product space, right? This is like 0 1 uh, product 0 1 and so on, and uh, the resulting space will convey all of the pairs or triplets or quadruplets or all of the other combinations. So for example, I will have like a tuple with 0 0, right? as my possible initial state, or a tuple with, let's say, 1 0 as my initial state, and so on. And what I want is the function that will map these tuples of multiple different bits uh, into some outcome, let's say 0 or 1. This could be, this is how we could design our oracle, okay? So if I have an unwanted state, let's say 0, 0 is the business solution encoding for the let's say answer that I do not want. That is why it will be 0. And if I want something, let's say I want this bit to be turned to as 1 because this is some kind of condition, and this is yet another condition, this will mean that, okay, I want this, and this encoding, this function, and in turn this oracle will trigger on this actual operation. So how do we do that? Well, we could say that, well, oracle is a black box, so we could be given this state from someone, because let's say someone designs an algorithm and we just apply it, right? Designs an algorithm for the oracle to search through this space for us. He does some operations on it, and then our job is only to append a Grover operator at the end to diffuse to alter these probabilities in the end, right? So we will take a sneak peek into this black box. So we will actually use a phase kickback to do this, because notice that we could, with this minus, right? With this minus, when we have an when we did a if you remember, we did something like this. We have prepared a 0, 0 state, right? We went into a bell state, so this was a plus plus, and we altered sorry, we went into this state. We went into this state, right? Sorry, not the bell state, because bell state is entangled. We were only doing a very simple. Let me actually draw it somewhere where it is black, so I could draw it clearly. In the phase kickback, what we did is we started with 0, 0. We apply Hadamard on our qubits, and before we did that, we actually went and flipped one sign to 1, because we prepared a 0, 1 state. We were missing this one, so we applied an X gate. So from that state, we applied a Hadamard on both qubits, right? And we ended up having this state, Hadamard tensor 2 on both qubits. And then we say that when we apply a control X, something magical happens, because our plus is being given a minus. And we can actually propagate it to whatever, what is insanely nice is that when we have an identity matrix, for example, 1, 1, 1, 1, 1, 1, 1, 1, this will be our state, which is I tensor 3, right? Because we have here there are zeros, This is a diagonal matrix. So we have, when we have I tensor free, we can actually pick a single point here and apply a minus here. If we know a right combination of state, let's say the fourth bit will be which one? Well, let's start from here. 0, 0, 0, 0, 0, 1, and so on and so forth. So here will be a 0, 1, 1. If we can apply conditionally on this state our let's say our change, the change, the minus, this would be insanely good because this will be our marking. This will be our marking. And how we can do this? We can do it with exactly this phase kickback system. We would need an extra qubit here to condition into that one single state that we can pick from identity matrix to transform it into whatever we actually like, right? And this is how we can do it. If we have, if we want to prepare our state, this is preparation of our state, of our minus, right? So here we go from 0. We then apply an x, so we have 1. And then when we apply a Hadamard, so we have x, we have h, and then we end up with minus. We can, from now on this bit, we can propagate a phase to all the other qubits that we like. However, look at this. We could, after the operation, we can recoup this, recover this, not recoup, recover. That would be the actual term. So after that operation, what we can do is I can go back with h into my 1 and yet another operation with x, and I have 0. I have made this qubit reusable as well. So that is really nice. But here, up here, already I did what I wanted. So what did I do here? When this qubit is 1 and this qubit is 1, I can apply a negative 1. And since we always apply an I operation, I operation, I operation, you just don't see it, but it is always applied. This is always, you can pretend as if it is always here. So here, 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 identity. I won't draw it way further than this, but there are all identities. So in other words, I have just applied on identity matrix my marking. This is actually it. With this simple operation, I could mark. I could even mark something else or more than one element. How can I do this? Suppose we have a 3 qubits, right? Let's say 3 qubits, right? I have it here, here, and here, let's say, and I make it. Here I will actually state that this is already a cat minus, and here I state that This will be a 0. Oh, this is a simplification, right? You already know the idea. This is my ancilla qubit. Here I applied a negative phase onto the last bit of the I3 matrix, I tensor 3 matrix. So this will be like 1, 1, something, 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 and the last element will have -1 in here. However, I could do the same right after, right? So I could prepare yet another state negative and recuperate it yet again. Here, however, what I could do is not apply, is instead of applying it to the absolute last state, so a 1, 1, 1, I could apply it to the state that is 0, 1, 1, because I could use the trick that we have heard today with our conditional marking, with our conditional execution of the with our preparation of any state besides 1, 1, 1, right? So we could flip, if this will be 0, uh, this entire ensemble will trigger because this X gate will flip it to 1, then this condition will apply, this condition will be satisfied, and after the last X gate, I will recuperate this bit into its original state for further calculation down the line. And this method of applying any amount of gates and marking any amount of elements that we would like to search for is actually really vital here in this case. Remember, this is very simple scenario. We mark integer for let's say not really the reason that we would like it to be performed in actual business situation, because we wouldn't use quantum resources to just search for integer when we know it exactly. Because when we know it exactly, as here, for example, we mark the 8th because we would like to search for 8th element. Well, this is a toy problem. There could be, and I will showcase you, there could be slightly more advanced applications where we do not know straight away what will be marked during the execution. I will actually showcase this project to you today. So this is the marking step, right? And this is how we can take a sneak peek into Oracle. We did that. We showed that we can mark a last element by performing a phase kickback from the auxiliary qubit that we had, that we prepared exactly for this purpose. We marked the state. Uh, we marked the state with it. So here we mark a state 1, 1 in our solution space. This is our original solution space, right? There will be, before this operation, this is only like a single sub-circuit, let's say, that it is like a zoomed in version uh, of our oracle, and only our oracle. But before it, expect that there would be some Hadamard gates to have an actual equal superposition of any solution. So this would be a prep step, and now we are looking at the at our query step. So this is the query step, right? What happens next? Well, we did mark. Now what? we have to apply a ginormous, let's say, we have to apply a ginormous matrix. There is a lot to it. If you see, there is like 7 steps. So this is a lot to take in. And there is really no good way to summarize it rather than just toying with it example by example. However, it doesn't change for any uh, Grover algorithm. This operator stays the same. No matter what oracle you throw in at the front, usually this operator stays in, and it is actually standardized and is available to be imported directly from the Qiskit. So you also do not have to make it yourself as we will make it, the same way as we will make it. So that's also very nice. However, and here are the actual calculations that follow this. So here we see that it is a very similar operation to what we did, right? This really resembles it. So for example, I said that we needed to have a certain level and then go twice with the number that will be the difference, right? So there is 2 times something, 2 times diff, and there is some initial state, right? Some initial state A. Um, what did we actually do in this notebook? Let's go back. Um, this is our, yes. So this was our initial solution. So as you can see, there's element plus 2 times diff, and this allowed us to perform this diffusion. And diff was actually when we unroll this meaning that we will actually perform this straight here. Oh, so as you can see here is our difference. When we refactor this equation, we could get something that resembles this. So we have identity and then some 2 times the actual difference. And this entire operator, this entire matrix that results in this linear combination of the 2 matrices is also called a diffusion operator. So we could say Grover operator, Grover diffusion operator, all of these matter the same thing. All of these mean the same thing. And what we do is that we diffuse with this. This will be our result of performing it, or of performing of preparing that operation onto qubits. And so this entire operation, I will actually print screen, go to paint. So forgive me for slight inconvenience with new, don't, so forgive me with my absolutely bright screen for a moment. Let me go back to our operation. right about here. So this is what we do. Um, we can see that we apply H to everything other than ancilla. We apply X to everything other than ancilla. We apply multiple control not operators. So here, since we have 2 bits only as control, we apply them on the on our 2 qubits. In general, it means on the qubits that represent our solution space, right? There will be more of them. That is why there is a wording ancilla qubit is target and all other qubits are used for controlling. So notice this, set ancilla qubit to -1. So we invert the phase. So what we want to do is not only to, let's say, prepare this matrix where every single entry is 1/n and so forth, but we also want to perform an operation that will mark middle elements. And since we have h qubits on all of the on the entirety of our solution space, this is what we get here, right? We have this phase key, but if I didn't have this, this would have been a completely different matrix. Um, yeah, so I will go through them at the end. Okay, I will go at the end because we are very close. So what do I do here? I prepare every single operation that I have listed. And then we use this, coming back, I use the phase kickback. Then I revert because the entire idea is to apply the phase kickback. And then, as you can see, we actually revert. So this operation of reversing, applying some operations, some preparations, in terms of even this Grovers, right? This is a prep stage. This is some operation that we would like to apply, and then we revert again. But the damage is already done at this step. This is really, really, really common throughout absolutely many um, in absolutely many situations. And then we after we do this, so we also apply the ancillary. Okay, so this would be something else. So here we reverse the operations um, on the actual on our actual solution space. So other than the Scylla as actual is our actual solution space, right? So other than the Scylla, it encodes this phrase encodes our solution space. So we apply this operation. Then what we do is we try to recuperate this ancilla qubit. So we first set it to our minus, and at the end we also recuperate this. I'm sorry, I have right. I have so this is the ancilla. Uh, this we apply it as a part of this operation, of this special operation during the calculation. So this is entire prep, including the ancilla, and this is entire uh, recovery after we apply the operation. So OP prep again, and recovery. Uh, this is more for you to understand how do these algorithms operate on. I am not sure about other algorithms. For example, let's say, how does, let's say, quantum neural network operate? Uh, I think that you will be able to ask these type of questions. How does it compare to what we do in quantum neural networks at 11th October during the yet another quantum workshops that is underway. If you would like to, you can register and ask these type of questions. I am not as experienced to answer this question for you, but this is like besides the point. The entire Grover operator applying the diffusion will look like this after we do every single of the af after we do every single operation that was listed. So preparing the superposition, then um, performing the superposition, then marking, and then yet again recuperating. And now, after all of this, this is actual state that we did, right? So here I apply the inversion. So this is why that operator compared to this is my solution for the task 3. My solution compared to what is listed here differs by one thing, and it is actually listed in the task, I think, because the ancilla qubit is not set throughout this operator. This is only the one operation that is here is set. So I could actually oh actually work actually performed right here. So for example, um, here was our prep, here was our execution, and here was this recovery, right? But I did skip the minus state preparation. So minus state preparation is here. Then we do inversion, and then what we do is we go from 0 on ancilla. Ancilla is 0, so we make it as negative. And since now ancilla is a negative, we want to make it as 0. So this is the last two steps, right? And the entire circuit looks like this. So yet again, here is our minus preparation, now visually. Here is our entire inversion. And here is going from 0 to minus is here. I will actually mark it with green. This will be slightly more helpful. I will draw over it slightly. And here we have a from minus to 0 in yet another way. So previously we have seen code, we have seen mathematical example, and here in this way we see it graphically. Three different ways to represent the same thing, right? Okay, so what happens when we tie everything together? So that is it. There is Grover. We have equal superposition of our on our circuits. I define my circuit as here as I defined my circuit like this. It could have been, for example, two quantum registers, because one quantum register would be called a plainly solution space. The other quantum register could be plainly named as ancillary register. Yet another could be yet another ancillary register for ancillary register 2, for example, for conditional statements, right? And yet another. And we could pass into quantum circuit many registers. This isn't the limitation that we would need two of them. But here we have everything coming together. Set ancilla, I will remove this because I have uh, coded it quite differently in this. So this is the diffusion. This will be our query step diffusion step. So diffusion inversion step, right? As I said at the first, and then our measure step. So this is how it looks like. The entire circuit. And yet again, the same thing. So here, visually. Here is our state preparation, prep. Now preparation of our initial solution. So preparation of our entire circuit. This is our oracle, right? So this entire box would be our oracle that we kind of treat as a black box, but we uncovered what it actually means, and it doesn't. I hope it doesn't mean uh, this. It isn't as difficult. Then we have a inversion, and I think I missed the X operation here. I do think that I did miss this. So here is our inversion, or rather Grover operator, GOP, oh, GOP, oh my God, I mess so much, operator. And here is the final step, which is I will make it as black because black and white does look pretty nice. And this is our measure. And as you can see, since we marked what we did mark, we mark 1, 1. Uh, so look what happens after all of this processing. We only observe 1, 1 as our final answer. If this was a 3-qubit situation and we had yet another qubit here up here somewhere, and we tagged in this control yet again, what would we had? What would we get? Can you answer this question? If we had one more qubit in our solution space. So, for example, we know that in the base case, we mark 1 1 as a state, and we get this as our observed. If we had one more qubit and we marked this, because so far we mark 1 1, and if we had one more qubit and kind of tie it together, what we would mark here in this state, we would mark 1 1 1. Yes. And what would we get as our solution? Yes, this is also true. We have 8 possible states now, but I would like to uh, only consider the part where uh, your intuition starts to kick in, right? So what would be if we mark only one state and we perform this operation and we mark 1 1 1, we have exactly the same situation as Robert said. So we get 1 1 1 as our state. If we have marked two states, let's say 1 1 1 and 0 0 1, then we would have 50-50 of those two solutions. However, when we also tie in the situation with different things like, let's say, oh, it's actually eight states now, right? So we have not perfect amount of iterations for it, because when we search one state out of the 8 outcomes, we don't get actually like perfect nullification of those unwanted answers. So we will have some counts towards these unwanted answers as our result. So so if 1 in 8, then it wouldn't be so easy. That is also correct answer, but we would have a when we had this extra qubit, we tie it together. It means that we mark 1 1 1. So we boost 1 1 1, right? And we try to nullify, let's say, and we nullify not 1 1 1. So for example, 0 0 0 will be way less common in this after the measurement in our shots. So that's the entirety of the explanation of the um, let's say Grover algorithm that I wanted to show you today. Thank you for attending to this in this workshop. I hope you liked it. I hope this wasn't too much, but if it was too much, don't worry, it was too much for me as well. But I hope you will get there sooner or later. The quizzes are actually way easier and doesn't require you to draw out, for example, 3 pages of equations. Um, Even if there are equations, they are pretty simple to solve. So how does quiz work? The Mr. Afik, I'm sorry if I butchered your name, um, asked 3 questions regarding the quizzes. So how do they work? You have 3 attempts per each quiz, um, and only um, the best outcome matters. So if you have, let's say, if you have got 14 points out of 20, and your next attempt is 10 points out of 20, so you made it worse, the best result still applies. So you don't have to worry about it too much if you have burned one of your attempts as, let's say, going lower than previous, because only the best result applies. Second question. Each quiz is based on the material from each lesson. Yes. However, there was some question that I have seen in the Discord about the day 3, which required the Q60 notebook knowledge. And on the day 3, we only go up to notebook 52 in terms of the agenda. So there is some ambiguity. However, there is already you have already attended all the material that there is. If you have attended every single lecture, if you have not, then the lecture from today will be available at the Discord in some time. I suppose it will be like half an hour or an hour or something. It depends when it will be prepared, but every single lesson is available to you. So there is no pretty much there is no, even if there is some ambiguity, you already have all of the answers for all of the questions in terms of all of the material has been already laid out. In terms of if Jupyter notebooks are enough for a preparation, yes, they are. If some of the tasks are marked as challenging here. So for example, here a task 5 is challenging. And this is something that, yes, this is really challenging. And in terms of actual Grover diffusion, it wouldn't be as challenging to make it, but for example, designing, let's say, Oracle for the case of 3 qubits, it could be very challenging. It could be very challenging to, for example, designing a Grover operator yourself if you only use a circuit primitive. So for example, if I only use a circuit.ccx, sorry, uh, to perform and to make this big inversion, then yes, it is very hard. But I have showed you yesterday the method of how to make a better construction, better control construction. So there it is. This is yes. So this is it. So for example, you could instead of this QCirc, it could be directly your solution. So you just uh, want to import an XGate from the main library and pass in, like instantiate the XGate and use its direct method, which is called control. Okay. And this control is like control number. You can pass in 5, 6, 8, whatever. And then you use it like this. This will be your target circuit. So you can even completely disregard of these operations and use it like this. So this will be your quantum register that will be your um, your control bits, and the last bit, in this case, the ancilla, even if it is a quantum register, you can unpack it with the star operator in Python, and this will unpack it in terms of giving you a single qubit. Because what I pass in is a list of qubits in order. So first qubits will be control qubits, and the last qubit, this was a quantum ancilla actually. It will be a control qubit. So here it is. And this is way more simple definition of control gates rather than what you have been doing with pairing up. As I said yesterday, when you do a CC, CC, and for every single one you have used a CCX, and you needed an ancilla qubit, ancilla 1, then this was ancilla 2, and both of these ancillas then combine into yet another CCX into your target, right? So this is way more complicated construct. You don't need to do this. There are primitives in the library that can help you. Uh, so I have diverged like very heavily, and yeah, I have diverged like really heavily. But anyway, I'm sorry. I like to talk a lot. I hope you get something from it at least, right? And you get something more than is in a base QBronze, okay? This was also my aim at this throughout. I'm sorry, not at this, throughout this workshop, that you get something more than just a Jupyter notebooks, because just Jupyter notebooks, you could have done this yourself and also arrived at a pretty satisfying answer, but of of course passing, but you would not have had, for example, some extra information. And yes, the Jupyter notebooks are enough for this. There are a ton of equations. There are some very simple tasks for you to do, to implement. Some of it is partially implemented for you. So for example, here, I didn't write this. This was already provided by the project creators for you to understand and to present you some more, let's say, some slightly more advanced uses. So for example, here is a CCCX using only the primitives from the library, from the circuit, right? So how to combine these gates. Here is a control node, but for example, here is presented uh, with respect to which bit is set as 1 or which bit is set as 0. So these are the subscripts. So this is C0, C1, C1, C0 means that I apply X only when the state is 0, 1, 1, 0, right? So these are the subscripts. And this is also um, in notebooks. So any ambiguity should be solved. Okay, so last 8 minutes. I will present it to you something fun if you would like to. If you want to take a break or something, that's a good time to take it. I don't hold you any longer. You could consider yourself, if you apply everything that we have been doing here, if you apply it into some of your, let's say, projects, or you make some fun projects like I did, For example, I did a personal project that is a that I called Easy Grover, and this is pretty much this takes the knowledge from the let's say this takes the knowledge from QBronze and QNickle to extreme, let's say, and we can say that it is. Let me actually take a sip of. Let me take a sip of a tea. So this is what you would do on the QNickle. Uh, in this in QNickle, you are tasked with slightly more in developing Grover algorithm for slightly more in depth, and you are given a history of it. So, for example, how did they discover this step by step, and how did Grover went into his final solution? So, for example, what you can hear about, what you can learn about is Joe's algorithm, Bernstein-Vazirani algorithm, if I pronounced it right. And with these steps, with this, also these are toy problems. These are not something that you solve in business, but these toy problems lay out to you the progression of getting a depth into the Grover's algorithm, and then at the end you apply it to this. So in here, what I have is I will actually make it as a presentation. Let's not distract ourselves with this. I will make a view enter presentation mode. So I will cut this out for now. So what you are tasked with during the actual, let's say, during the QNickle is to solve a problem of graph interconnectivity. So suppose you have nodes and you have links between them, which are called edges. There is a certain algorithm that you can do that makes these nodes take certain colors. Let's say this will be yellow, this will be yellow as well, and this will be red, and this will be also red. So there is certain pattern that you could color. You could color, for example, with you could apply one color to a let's say one node, and then whatever else is connected to it will have a completely different color. So if I have this situation where I have a red node, my linked partner will be a yellow node. And the idea is to find not only a single combination or let's say a let's say or optimal combination, but to find all of them. Or for example, I could say that, oh, you know what? I don't want this. I want this to be a, oh, I have actually, I have actually removed it. So what happens here is that we call it a graph cut because the cutting happens whenever we have two different nodes connected to each other. There is a cut. So I could remove this node, this link and this link. And now what happens is that I am left with one link. I could modify my problem to find these different permutations of the entire graph and the entire links. And what is good about it in terms of quantum computations is that the entire my solution space are the nodes, and I could condition between the nodes, between these qubits, to mark whether there is a connection or not. And I could, for example, search through that space and through my ancilla qubits like this to perform something more advanced, and I could search for only the combinations of these nodes that solve my problem that I posed. And what is my problem? For example, if I go back, let's look at the number of nodes and the problem. So I have 4 nodes, right? I have 4 nodes, and this is 0, this is 1, this is 2, this is 3, and I have some edges. So 0 is connected to 1, 1 is connected to 2, and 3 is connected to 2. And I could, in my quantum circuit, make certain combination of gates that represent this problem and tracks every single marking on my during my iteration, during iterations. And after the iteration, what I get is the answers that solve my problem. So after I perform every single operation, I have made it such easy that I can just call a graph cut and that's it, and cut solve. Uh, I also have something else to show you, which is oh, this is actually my circuit that I see. You see that it is way more complicated, right, than what you have seen during this course. There is good reason for it, because there are many more operations that we would need to do. But hey, there are actually some operations that are very that are similar. Since look at this, what I have are exactly the same blocks that we have been talking about all this time. I have the block for measuring. I have the block of preparing my state. And this entire thing, I will mark it as another color. It actually wraps up into the other edge. This is like moment 0, right? This is moment 0. This is moment x. This is moment x plus 1 in the quantum machine that performs all the operations. And this is some moment, last moment. So I will call it -1. So even in this ridiculous, for you it might be ridiculous, but for me it is very simple actually. In terms of the complexity, there are way more. You could go way beyond this. Um, and this entire thing, in green is actually an oracle that performs some checks, and all of these are, for example, here. These are my solutions. So solutions. These are qubit that encode solutions. And these all qubits, these all other qubits are ancilla. So look how much I use, right? I use incredibly many. So these are ancilla. That are used to, for example, mark the edge, mark yet another edge, yet another edge. There is some sort of concept of adding. There is my, for example, phase flip, right? This is something, and I propagate it throughout the circuit. And hey, here it is, our Grover operator, which we are already familiar with, Grover. So even in these complex situations, we can still see some of the basis blocks that we deal with. and that I taught you during the QBronze. So that state preparation, the oracle, the grover, and the measurement. So I won't go much further into explaining what every single operation is there. Okay? But here I hope I convinced you that this is something more, this what you have learned is something that happens actually in, let's say, uh, in actual, like there is a use for it. That's the one thing. And some of the blocks that you have already internalized or you may internalize in future can already be distinguished like this. Here I did also make it easier for you by appending the barrier and easier for myself as well, because this is sometimes I debug like this by separating the instructions so that they don't clutter together, right? And this is this is pretty much it, right? Four operations, four blocks, four operations. This one, this ginormous thing, which continues on and wraps onto the other side. This thing, which you already know, this is Grover operator and measurement. Four blocks, even in this way more complex case. So I hope you like this. There is yet another thing which you could do, and this is to evaluate your secret depth and performance. You could um, also, this is also a sneak peek to some, for example, quantum hackathons that have took place. This is something that I have uh, made based on the IBM's 2019 challenge. This was actually very similar to the graph problem, but what they did is that they evaluated solutions based on the depth of the circuit. The shorter the depth, the better the solution. Because remember that we have these errors, so when the circuit is shorter, there is less instructions, so there is less chance to mess up. And there is a certain operation that could um, tra transform your entire circuit into very basic operations, and counting those operations could give you the idea of what would be the actual impact of your experiments, and will you have something really nice as a result, or you will see that, oh, there is 68 conditional X gates. So, well, maybe this won't work because there will be some sort of an error happening. So these are also things that you could do to judge execution of your entire solution. And this is something that also doesn't happen in QBronze. You are not required to know this. What I did here is only to show you something extra as the end of the workshop. So here marks the end, and an actual end, I promise. I really promise. Um, Here actually marks the end of the workshop. Here is also a proposed answer, so my algorithm both work because these were, if you recall, this was our um, graph, and 1 means another one color and 0 means another color. So for example, I will color 1 with this and leave zeros as empty. So this would be one solution for full cut, meaning that I cut this, and I cut this. Since as you can see, each one is has a neighbor each node has a neighbor that is different color than itself. And there is yet another permutation to this where I could draw it like this, right? This is also another valid permutation. That is why there are two answers. So that's the end. How did you enjoy this? I can accept answers here in chat. I can accept answers in Discord. If you have any questions that are, for example, finishing remarks, now it's a good time.
So, Mateusz, by the way, I'm also going to send a feedback form to participants. So,
Oh, that's nice. That's nice. That's nice. Okay. So are there any like questions that you would like to ask me before we finish? Or is it like some sort of clarification for any of the previous lectures on the previous days? Because that's like the last time to have it also in the video form for the future reference. It would be a nice time to ask. If you want, you can also uh, uh, let's say enable voice and ask directly if you're not shy. Yeah. There, the entire Discord space has been created for you. So if you have, for example, more complex question that would be too long to answer now, you could ask it in the next day, just ping me in the Discord. Or if it is something else, you could also ping the mentor. It would also be kind of good. But any specific questions, yes, we are here to help you. Yeah, that's also a good attitude to raise more questions once you get through the material, like at your leisure, because there was a lot of the. I repeat this all the time. There was a lot to take in during these 15 hours because I went over and also explain you more things than in QBronze, than the base material. There is also a channel for for question and answers, like voice chat, right? So you could kind of uh, probably have let's say uh, a question and do it like this. You post a question or you ping me that I would like to, for example, hear from you, and we could pop in the voice. You don't have to be active in terms of voice. Uh, I could explain to you with my voiceover, right? And then the only thing that is left is whether you will be satisfied or not. So if you have no questions, I think we can wrap up. So we could stop the video. I will stop screen sharing right now. And yeah, thank you for joining me. Oh, there is a question. I believe if we approach with physics and math we can do something fabulous. I think quantum computing is the best option, but my question is it possible? Well, yeah, it is possible. The question for you, the only thing that matters, that would matter, will be if you find yourself in this. If you find yourself in this, if you enjoy this, then hey, why not try? But if you want and if you won't try, you won't know, right? You wouldn't know this if it is possible, if it is also enjoyable for you. Um, Even at a high school graduate level, at a high school graduate level, I would expect that this would be pretty hard actually to do all of this. Um, I have some calculus under my belt, but this was like only level like I would I have graduated from chemistry, not from any physics, any math, any IT. I have graduated from chemistry, so I could get this, but also during the engineering studies, I also had some higher level mathematics. I had derivations, I had matrix operational matrices and so on. So this wasn't that uh, far off. But for you, it might be harder if you didn't do this. But everything comes with time. So the QBronze certifications, usually we hand these out after all of the deadlines pass, because there are some late submissions. There were historically late submissions to even last year QSilver workshops. QSilver are way harder, by the way, than this one. So that's also quite understandable. But in terms of the certifications, we usually hand them out after every single deadline for every single quiz passes, because we would like to give the opportunity for the students to fill in the quizzes. So you will most likely they will be handed out week after 1 week after the end of the last deadline, I would say. Is it correct, Pavel?
Could you please repeat?
When do we hand out the certifications?
Usually it takes about 2 weeks after the deadline for the last quiz.
Okay,
So
okay.
in
So
this
here's your
case, I
answer.
expect that it should happen at the beginning of November, maybe end of October.
So it was a question from the chat.
Mm-hmm.
So I stopped my screen share and we can wrap this up. The last
Okay.
part.
Thank you, Mateusz. Thanks for all these 5 days of the workshops. Thanks for conducting them. And I hope that everyone enjoyed. Hope that you learned a lot and had fun. Um, yeah, just a reminder about the quizzes. So there are some deadlines, so please check the canvas. If you want to get a certificate. And once again, we invite you to attend the Warsaw Quantum Computing Group meetup on Thursday, Quantum Machine Learning Workshop on Saturday and Sunday, and QPoland Global Quantum Hackathon starting on October 18. So we hope that this is just a beginning of your quantum journey, and you will join us for our next event. And as I said, I will later send you a feedback form. And you can also share your feedback on our Discord channel. Thanks once again. I will now stop recording.